Tonight, we're going to talk about something that sounds like it belongs in science fiction, but is absolutely real. There is a particle out there that is almost identical to the electron. It has the same mass. It spins in the same way. It behaves in nearly every respect, like the electron that holds your atoms together right now. But there is one difference. One single property is reversed. And because of that reversal, the moment this particle touches ordinary matter, both particles cease to exist. They don't bounce off each other. They don't merge. They are completely erased, converted entirely into pure energy. No debris, no remnants, just light. It's called the positron. And what it reveals about the nature of matter is far stranger than you might expect. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with the electron, because you can't understand the positron without first understanding what it mirrors. The electron is one of the most fundamental particles in the universe. It's a building block of everything you see, everything you touch, everything you are. Every atom in your body contains electrons. Every chemical bond that holds molecules together exists because of electrons. Your thoughts, your memories, the electrical signals firing through your brain right now, all of it is electrons doing what electrons do. An electron is incredibly small. It has a mass of about 9.1 times 10 to the negative 31 kilograms. That number is so tiny, it's almost meaningless in everyday terms. To put it in perspective, if you gather together a billion electrons, their combined mass would still be less than a billionth of a gram. You'd need approximately 10 to the 25th power of them, a 1 followed by 25 zeros, just to reach the mass of a single grain of sand. Electrons are unimaginably light, and yet, despite being so small, they're responsible for nearly every phenomenon you experience in daily life. Light, electricity, magnetism, chemistry, biology, all of it depends on electrons. The electron carries a negative electric charge. This is one of its most important properties. Electric charge is what determines how a particle interacts with electric and magnetic fields. It's what governs attraction and repulsion between particles. Two particles with the same sign of charge push each other away. Two particles with opposite signs of charge pull each other toward one another. This is why electrons are attracted to the protons in an atom's nucleus. Protons carry positive charge, electrons carry negative charge, opposite charges attract. That attraction is what holds atoms together. Without it, atoms couldn't exist. Without atoms, nothing you see around you could exist. Chemistry, biology, solid matter, all of it depends on the electromagnetic attraction between positive protons in the nucleus and negative electrons surrounding it. Now, here's where things start to get strange. Imagine you could take an electron and flip its charge. Don't change anything else. Keep the mass exactly the same. Keep the spin exactly the same. Keep every other property identical. Just reverse the sign of the electric charge from negative to positive. What would you have? You'd have a positron. That's essentially what a positron is. It's an electron with a positive charge instead of a negative one. Same mass, 9.1 times 10 to the negative 31 kilograms. Same spin, 1/2 in the units physicists use. Same magnitude of charge. But the charge points in the opposite direction. The electron is negative. The positron is positive. That single reversal changes everything about how this particle interacts with the universe. This might seem like a small difference, After all, the mass is the same, the spin is the same, the magnitude of the charge is the same. How much can one sign change really matter? The answer is that it matters enormously. It matters so much that it determines whether the particle can coexist with ordinary matter or whether it will be annihilated the instant it encounters an electron. That one reverse property is the difference between existence and total destruction. But let's slow down. Before we talk about what happens when a positron meets an electron, let's talk about how we even know the positron exists. Because here's something remarkable. The positron was predicted before anyone had ever seen one. A physicist figured out it had to exist using nothing but mathematics. No experiment, no observation, just pure theoretical reasoning. And when experimenters went looking for it, they found exactly what the math had predicted. This is one of the most stunning achievements in the history of physics, and it tells us something profound about how the universe works. In 1928, a British physicist named Paul Dirac was working on a problem. He was trying to combine two of the greatest theories in physics, quantum mechanics and Einstein's special relativity, into a single equation that could describe how electrons behave at speeds close to the speed of light. Quantum mechanics described the behavior of particles at the atomic scale. Special relativity described how space and time behave when things move very fast. It gave us E equals mc squared and showed that mass and energy are two forms of the same thing. Both theories were incredibly successful on their own, but they hadn't been properly unified. No one had written down an equation that described a quantum particle like the electron in a way that was fully consistent with Einstein's relativity. Dirac set out to do exactly that. What he produced was the Dirac equation. It's one of the most beautiful and important equations in all of physics. It described the electron perfectly, accounting for its quantum nature and its behavior at relativistic speeds. It even predicted the electron's spin, a property that had been discovered experimentally but had never been explained theoretically. The Dirac equation didn't just describe the spin, it required it. The equation couldn't work without the electron having a spin of 1/2. This was a triumph. An equation derived from pure theoretical principles predicted an experimentally observed property of the electron. That's the gold standard in physics. But the equation had a problem. Or at least, what seemed like a problem at first. When Dirac solved his equation, he found that it had two sets of solutions. One set described the electron perfectly. Negative charge, positive energy, everything matching what physicists already knew. But the other set of solutions described something else. Something that had the same mass as the electron, but with a positive charge and what appeared to be negative energy. Negative energy didn't make physical sense. A particle with negative energy would behave in bizarre ways. It would accelerate when you tried to slow it down. It would gain energy by emitting radiation instead of absorbing it. The universe would be fundamentally unstable if negative energy particles existed, because ordinary particles could keep dropping into lower and lower energy states without limit, releasing infinite energy in the process. Nothing would be stable. Everything would collapse. Most physicists at the time thought these negative energy solutions were just mathematical artifacts. Equations often produce solutions that don't correspond to physical reality. You throw them away and keep the solutions that make sense, but Dirac was bothered by this. The equation was too elegant, too perfect in its description of the electron for half its solutions to be meaningless. He felt that the equation was telling him something real about the universe. He just had to figure out what. Dirac initially tried to interpret these solutions as describing protons. Protons have positive charge, just like the mystery particle in his equation. But this didn't work. Protons are about 1,836 times more massive than electrons. The solutions to Dirac's equation demanded a particle with the same mass as the electron. Whatever this particle was, it wasn't a proton. Eventually, Dirac made a bold prediction. He proposed that there must exist a particle with the same mass as the electron, but with opposite charge. A positively charged electron, an anti-electron. He published this prediction in 1931, and the physics community was skeptical. No one had ever observed such a particle. There was no experimental evidence for it. It seemed like an extravagant prediction based on nothing but mathematical formalism. Then, in 1932, an American physicist named Carl Anderson was studying cosmic rays. Cosmic rays are high-energy particles from space, protons, atomic nuclei, and other particles that constantly bombard Earth's atmosphere. When these cosmic rays hit atoms in the atmosphere, they create showers of secondary particles. Anderson was using a device called a cloud chamber to photograph the trails left by these particles. A cloud chamber is essentially a sealed container filled with supersaturated vapor. When a charged particle passes through the vapor, it ionizes gas molecules along its path. These ionized molecules act as seeds for tiny droplets of vapor to condense around, creating a visible trail. By placing the cloud chamber in a magnetic field, Anderson could bend the paths of charged particles. The direction and amount of bending revealed both the charge and the momentum of the particle. A negatively charged particle bends one way. A positively charged particle bends the other way. A heavier particle bends less. A lighter particle bends more. Anderson saw something he couldn't explain. A particle track that curved the wrong way. The amount of bending showed it was too light to be a proton. It had to have about the same mass as an electron, but the direction of the curve showed it had a positive charge. Not negative like an electron, positive. Anderson had found Dirac's predicted particle. He called it the positron, short for positive electron. He published his discovery in 1932, just 1 year after Dirac's prediction. This was a watershed moment in physics. A particle predicted by pure mathematics was found to actually exist. The equation was right. The universe really did contain a mirror image of the electron. Anderson received the Nobel Prize in Physics in 1936 for this discovery. Dirac had already received his Nobel Prize in 1933, partly for the theoretical work that led to the prediction. Let me be clear about something because it matters for understanding why the positron is so significant. The positron is not a hypothetical particle. It's not theoretical. It's not something physicists think might exist. It is as real and as well established as the electron itself. Positrons have been produced in laboratories millions of times. They've been detected, measured, and studied with extraordinary precision. Their mass has been measured to agree with the electron's mass to better than 1 part in a billion. Their charge has been measured to be exactly equal in magnitude to the electron's charge, but opposite in sign. Everything about the positron matches the electron except for that one critical difference: the sign of the electric charge. Positrons are being produced right now as you listen to this, all around you. Certain radioactive elements produce positrons when they decay. Potassium-40, which exists in small quantities in bananas, in your bones, in the soil beneath your feet occasionally undergoes a type of radioactive decay called beta plus decay, in which a proton inside the nucleus transforms into a neutron and emits a positron along with a neutrino. The positron flies out of the decaying atom at high speed and almost immediately encounters an electron in the surrounding matter. When it does, both particles are destroyed and 2 gamma rays are emitted. This is happening right now inside your own body. Tiny amounts of potassium-40 in your muscles and bones are producing positrons. Those positrons are meeting electrons and annihilating. Your body is experiencing matter-antimatter annihilation at this very moment. The amounts are incredibly small, far too small to affect you in any way, but the process is real and ongoing. Cosmic rays striking Earth's atmosphere also produce positrons. When high-energy particles from space collide with air molecules, the energy of the collision can create new electron-positron pairs. This is called pair production, essentially E equals mc squared running in reverse, converting energy into mass. But the universe never creates a positron alone. Conservation of charge demands that a positron with its positive charge always appears alongside an electron with negative charge. They come in pairs, always balanced, always equal and opposite from the very first instant of their existence. Hospitals use positrons every day. If you've ever heard of a PET scan, that stands for positron emission tomography. A patient is injected with a substance that contains a radioactive isotope, often fluorine-18, which emits positrons as it decays. Those positrons travel a very short distance, usually less than a millimeter, before encountering an electron in the patient's body. The 2 particles annihilate, producing 2 gamma rays that fly off in opposite directions. Detectors surrounding the patient pick up these gamma rays. By analyzing where the gamma rays came from, a computer can build a 3-dimensional image of where the radioactive substance accumulated in the body. This is how doctors detect cancers, study brain activity, and diagnose heart disease. Every PET scan is powered by matter-antimatter annihilation happening inside a patient's body. Positrons are produced, they meet electrons, both are destroyed, and the resulting gamma rays are used to create an image. The fact that we use antimatter in routine medical procedures shows just how real and well understood positrons are. This isn't exotic physics happening in some remote laboratory. This is happening in hospitals around the world every single day to diagnose and treat patients. Antimatter is not just real, it's practical, it's useful, it's mundane, in the sense that medical professionals use it without giving it much thought. Now, let's talk about what electric charge actually means in a deeper physical sense, because this is crucial for understanding why the positron's reverse charge has such dramatic consequences. Electric charge is one of the fundamental properties of matter. Along with mass and spin, charge is one of the labels that define what a particle is and how it interacts with the rest of the universe. Charge determines how a particle responds to electric and magnetic fields. A charged particle in an electric field feels a force. The direction of that force depends on the sign of the charge. A positive charge is pushed in the direction of the electric field. A negative charge is pushed in the opposite direction. This is why the positron behaves differently from the electron in electromagnetic fields. If you put an electron and a positron in the same electric field, they accelerate in opposite directions. The electron goes one way, the positron goes the other. In Anderson's cloud chamber, this is exactly what revealed the positron's existence. It curved the wrong way in the magnetic field. It had to be positively charged. But it was too light to be a proton. It had to be something new. Charge also determines how particles attract or repel each other. Two electrons repel each other because they both carry negative charge. Two positrons also repel each other because they both carry positive charge. But an electron and a positron attract each other because they carry opposite charges. This attraction is not some mild, gentle nudge. The electromagnetic force between an electron and a positron is exactly as strong as the force between an electron and a proton. It follows the same inverse square law. Double the distance between them and the force drops to 1/4. Halve the distance and the force quadruples. This attraction is what draws a positron toward an electron when they get close. And it's the first step in the process that ultimately destroys them both. The positron doesn't need to collide head-on with an electron. It doesn't need to be fired at high speed. The electromagnetic attraction between them will pull them together naturally. A positron released into any ordinary material will be drawn toward the nearest electron. The attraction is inescapable. Wherever there are electrons, and in ordinary matter, electrons are everywhere, the positron will find one. And when it does, the consequences are total. But charge is not the only thing that distinguishes the positron from the electron. There are other quantum properties that are also reversed, and these play a crucial role in what makes annihilation possible. We'll explore those shortly. For now, the important point is this. The positron has the same mass as the electron, the same spin, the same magnitude of charge. But the sign of that charge is reversed. And this reversal is not cosmetic. It's not superficial. It defines the positron as something fundamentally different from the electron, something that cannot peacefully coexist with it. Let me give you an analogy, though like all analogies for quantum physics, it's imperfect. Think of the electron as a key and the positron as the exact negative mold of that key. They're made of the same material. They have the same shape, but one is the inverse of the other. If you try to put them together, they fit perfectly. Every notch on the key fits into a corresponding ridge on the mold. Every ridge on the key fits into a corresponding notch on the mold. They don't bounce off each other. They don't simply coexist side by side. They fit together so perfectly that they cancel each other out entirely. That's what happens with the electron and positron. Their properties are so precisely opposite that when they come together, they cancel completely. Nothing is left but energy. This is what makes the positron so extraordinary. It's not just another particle. It's the electron's exact opposite. Its perfect mirror. Its antimatter twin. And the universe, it turns out, has a rule about what happens when a particle meets its antimatter twin. They cannot coexist. They destroy each other utterly and completely. The mass of both particles is converted entirely into energy, following the most famous equation in all of physics, E equals mc squared. The m is the combined mass of the electron and the positron. The c is the speed of light, about 300,000 kilometers per second. And when you multiply that tiny mass by the speed of light squared, you get the energy released in the annihilation. Each electron-positron annihilation releases about 1.02 million electron volts of energy, split between two gamma-ray photons. That might not sound like much, and for a single pair, it isn't. But consider what it means in terms of efficiency. 100% of the mass is converted to energy. Not 99%. Not 99.9%. 100%. Nothing is wasted. Nothing is left behind. No other process in nature achieves this. Every other energy source, from chemical combustion to nuclear reactions, leaves most of its mass untouched. Matter-antimatter annihilation leaves nothing. The conversion is total. It is the most efficient energy release process permitted by the laws of physics. A direct and complete transformation of mass into radiant energy. This efficiency is a direct consequence of how perfectly the positron mirrors the electron. Every quantum number is exactly opposite. Every property cancels. There's nothing left over. No residue, no waste. Just pure radiant energy escaping at the speed of light. The positron's existence tells us something deep about the structure of the universe. It tells us that for every type of matter particle, there exists an antimatter counterpart. The electron has the positron. The proton has the antiproton. The neutron has the antineutron. Even the neutrino, that ghostly particle that barely interacts with anything, has an antineutrino. This symmetry runs through all of particle physics. It's not optional. It's required by the mathematics that describe how particles behave. The same equations that predict the existence and behavior of matter particles also demand the existence of their antimatter partners. Dirac's equation didn't just predict the positron, it predicted the existence of antimatter itself. Every particle has an antiparticle. This is now one of the most firmly established facts in physics. Confirmed by decades of experiments at particle accelerators around the world. Antiprotons were discovered in 1955 at the Positron accelerator in Berkeley, California, by Emilio Segre and Owen Chamberlain. Antineutrons were found the following year. In 1995, physicists at CERN created the first atoms of antihydrogen, an antiproton orbited by a positron. By 2016, they had made enough antihydrogen to begin studying its properties in detail. But the positron was the first. It was the gateway to all of antimatter physics. Before Anderson's discovery in 1932, antimatter was a mathematical curiosity, an odd feature of Dirac's equation that many physicists dismissed. After the discovery, antimatter became an established part of physical reality. The universe contains a mirror. For every particle, there is an antiparticle, and when a particle meets its antiparticle, they annihilate each other completely. The positron is not exotic. It's not rare in any absolute sense. It's produced constantly by radioactive decay, by cosmic ray interactions, by pair production in the vicinity of strong electromagnetic fields. The reason you don't encounter positrons in daily life is not that they're rare or hard to produce, it's that they don't survive. The moment a positron is created in our matter-dominated universe, it's surrounded by electrons, in air, in water, in solid matter, in your body. Electrons are everywhere, and the positron, attracted to electrons by the electromagnetic force, will find one almost immediately. The encounter takes nanoseconds at most, often far less. The positron and the electron attract each other, spiral inward, and annihilate. Two gamma rays fly off in opposite directions. The positron is gone, erased by the very matter that surrounds it. This is why we say that matter erases the positron. It's not that matter absorbs it the way a sponge absorbs water. It's not that matter captures it the way a net captures a fish. The positron isn't stored somewhere inside matter, waiting to be released. It's destroyed. It ceases to exist as a particle. Its mass is converted entirely into energy. The electron that destroyed it also ceases to exist. Both particles are gone. What remains is radiation. 2 photons of light that carry away the combined mass energy of both particles at the speed of light. You might wonder why we don't notice this. The answer is that the individual events are tiny. The total mass annihilated in a single electron-positron event is about 1.8 times 10 to the negative 30 kilograms. The energy released, about 1.02 million electron volts. Sounds impressive in particle physics terms, but in everyday terms, it's vanishingly small. You'd need to annihilate trillions upon trillions of electron-positron pairs to produce enough energy to warm a cup of coffee by 1 degree. The positrons produced by natural processes around you are so few that their annihilation is completely undetectable without specialized instruments designed to find gamma rays of exactly 511,000 electron volts. The characteristic energy signature of electron-positron annihilation. But here's what makes the positron truly fascinating. Despite being destroyed almost instantly whenever it appears in ordinary matter, the positron is not a fragile particle. It doesn't decay on its own. A positron sitting in empty space, far from any matter, would last forever. It's a stable particle with no internal mechanism for decay. No half-life, no spontaneous disintegration. The positron's destruction is caused entirely by its environment. It's the presence of electrons, the presence of ordinary matter, that seals the positron's fate. In a universe made of antimatter, where positrons were common and electrons were rare, the electron would be the doomed particle. The physics is completely symmetric. Neither particle is inherently unstable. They only become unstable when they encounter each other. This symmetry raises a profound question that has haunted physicists for decades. If the laws of physics treat the electron and the positron identically, why does the universe contain so much matter and so little antimatter? Why didn't all the matter and antimatter created in the Big Bang simply annihilate each other, leaving behind nothing but radiation? We'll return to that question later. For now, let's sit with what we've established. The positron is a real particle with the same mass and spin as the electron but opposite electric charge. It was predicted by Dirac's equation in 1928 and discovered by Anderson in 1932. It is produced constantly and destroyed almost instantly whenever it encounters ordinary matter. The positron is matter's perfect opposite, and the universe cannot tolerate that perfection. When the positron meets its mirror image, both particles are erased from existence. It is the most complete form of destruction in all of physics, and understanding why this happens requires us to go deeper into the quantum properties that make the positron the electron's true antiparticle, because the reverse charge is only the beginning of the story. So we know what the positron is in basic terms. Same mass as the electron, opposite charge, predicted by Dirac, discovered by Anderson, produced constantly by nature and destroyed almost instantly by ordinary matter. But saying the positron is just an electron with a flipped charge is like saying a mirror reflection is just the same image pointing the other way. Technically true, but it misses something deeper. The positron isn't simply a particle that happens to have opposite charge. It is the electron's antiparticle. And that word, antiparticle, carries far more weight than most people realize. To understand why the positron is specifically the electron's antimatter twin, and not just some other positively charged particle floating around, we need to go deeper. We need to talk about quantum numbers. We need to talk about fields. And we need to talk about one of the most profound symmetries ever discovered in nature, A symmetry so fundamental that if it were ever found to be violated, essentially all of modern physics would collapse. Let's start with quantum numbers, because they're the identity cards of the subatomic world. Every particle in the universe carries a set of quantum numbers. These aren't numbers you can see or touch. They're properties, labels that describe how a particle behaves and what it's allowed to do. Think of them as the particle's fingerprint. No two different types of particles share the exact same set of quantum numbers, and these numbers determine everything about how the particle interacts with forces, with fields, and with other particles. You already know about one quantum number, electric charge. The electron has a charge of -1 in the units physicists use. The positron has a charge of +1. That's the most obvious difference. But charge is not the only quantum number that distinguishes them. There are others, and they're just as important. One of these is called lepton number. Leptons are a family of fundamental particles that includes the electron, the muon, the tau particle, and their associated neutrinos. The electron is a lepton, so are the muon and the tau, though they're heavier and less stable. Physicists assign a lepton number to every particle. The electron has a lepton number of +1. Every other particle in the electron's family, the electron neutrino for instance, also carries a lepton number of +1. Particles that aren't leptons, like protons and neutrons, have a lepton number of 0. And here's the key point. The positron has a lepton number of -1, not 0, -1. The exact opposite of the electron's lepton number. This might seem like an abstract bookkeeping exercise, like some label physicists invented just to keep their equations tidy, but it has real, concrete, physical consequences. Lepton number is a conserved quantity in particle physics. That means in any interaction, any collision, any decay, any annihilation, the total lepton number before the event must equal the total lepton number after the event. You can't create or destroy lepton number any more than you can create or destroy electric charge. It's like a cosmic accounting rule that is never broken. Nature keeps a ledger, and the ledger always balances. When a positron and an electron annihilate, the electron brings a lepton number of +1, and the positron brings a lepton number of -1. The total lepton number is 0. After the annihilation, you're left with 2 gamma-ray photons, each of which has a lepton number of 0. Total lepton number after, still 0. The books balance, the conservation law is satisfied. If the positron had a lepton number of 0 or +1 instead of the -1, this annihilation couldn't happen the way it does. The math wouldn't allow it. The conservation law would be violated. The fact that the positron's lepton number is exactly opposite to the electron's is not a coincidence. It's a requirement. It's part of what makes the positron the electron's specific antiparticle. There's another quantum property that's reversed, and it's subtler than charge or lepton number. It involves spin, and how spin relates to the direction a particle is moving. Every electron and every positron has a spin of 1/2. That number doesn't change between them. But there's a more refined property called helicity, which describes whether the particle's spin axis points in the same direction it's moving or in the opposite direction. Imagine a bullet spiraling through the air. If the bullet spins clockwise as it moves forward, that's one helicity. If it spins counterclockwise, that's the other. For massless particles, helicity is fixed. For massive particles like the electron, helicity can change depending on the observer's frame of reference, but there's a related concept called chirality that is intrinsic. In the weak nuclear force, one of the 4 fundamental forces of nature, chirality matters enormously. The weak force interacts only with left-handed electrons and right-handed positrons. This is one of the most striking asymmetries in physics. The weak force doesn't treat the electron and positron identically. It interacts with them in opposite-handed configurations. The positron's chirality, its handedness, is opposite to the electrons when it comes to weak interactions. This is yet another quantum number that is flipped. So the positron doesn't just have opposite charge, it has opposite lepton number. It has opposite chirality with respect to the weak force. Every single internal quantum number that the electron carries, the positron carries the exact opposite. This is what makes it the antiparticle. Not just one reversed property, but all of them. Every quantum label that can be reversed is reversed. The positron is the electron's complete mirror image in the space of quantum numbers. Now, let's go even deeper because there's a framework in physics that explains why antiparticles must exist and why they must have these precisely opposite properties. That framework is called quantum field theory, and it's the most successful theoretical structure ever built by human beings. Quantum field theory, or QFT for short, is the mathematical language that combines quantum mechanics with special relativity. It's the foundation of the standard model of particle physics, which describes all known fundamental particles and 3 of the 4 fundamental forces. The standard model has been tested with extraordinary precision. Its predictions have been confirmed to accuracies of better than 1 part in 10 billion. It is, by any measure, the most precisely tested scientific theory in human history. In quantum field theory, particles are not little balls flying through space. They're not tiny marbles. They're not even really objects in the traditional sense. This is one of those concepts that sounds simple when stated, but is actually revolutionary when understood. Instead, particles are excitations of fields. Think of a field as something that exists everywhere in space, at every point, at every moment, filling the entire universe like an invisible ocean. A field doesn't need to be disturbed to exist. It's always there, even in the emptiest vacuum. The vacuum of space isn't truly empty. It's filled with fields sitting in their lowest energy state, quiet but present. The electromagnetic field is one you've probably heard of. It permeates all of space. When this field is disturbed in a particular way, when it vibrates at a particular frequency and amplitude, that vibration is what we call a photon, a particle of light. The photon isn't a thing sitting in the field. The photon is a ripple in the field itself. You can't separate the photon from the field any more than you can separate a wave from the ocean. The wave is the ocean in motion. The photon is the electromagnetic field in motion. The same idea applies to electrons and positrons. There is an electron field that permeates all of space. When this field is excited in one way, that excitation is an electron. When the same field is excited in another way in a sort of opposite mode, that excitation is a positron. The electron and the positron are not excitations of 2 different fields. They are 2 different types of excitation of the same field. This is a crucial insight. The positron isn't something separate from the electron. It's the other face of the same underlying reality. They're like 2 different notes played on the same instrument. One is the fundamental tone. The other is its inversion. Different sounds, but produced by the same string. This is why the positron has the same mass as the electron. They come from the same field. The mass of a particle is determined by how the field interacts with the Higgs field, and since the electron and positron are excitations of the same underlying electron field, they interact with the Higgs field in the same way. Same field, same interaction, same mass. It's not a coincidence. It's a mathematical necessity, and this is why the positron has opposite quantum numbers. When you work through the mathematics of quantum field theory, when you write down the equations that describe how the electron field behaves and solve them carefully, you find that the field naturally supports two types of excitation. One type carries negative charge, positive lepton number, and left-handed chirality in weak interactions. That's the electron. The other type carries positive charge, negative lepton number, and right-handed chirality in weak interactions. That's the positron. The equations don't give you a choice. If the electron exists, the positron must also exist. If the field can vibrate one way, it can vibrate the other way. The mathematics demands it. This is what Dirac stumbled upon in 1928. Though the full framework of quantum field theory wouldn't be developed for another couple of decades. Dirac's equation, when solved completely, contained solutions for both the electron and the positron. He initially didn't understand what the second set of solutions meant, but the math was telling him something real. The electron field supports two modes of excitation. One is the electron, the other is the positron. You can't have one without the other. This principle extends to every particle in the Standard Model. The quark field supports quarks and antiquarks. The neutrino field supports neutrinos and antineutrinos. The muon field supports muons and antimuons. For every fermion, every matter particle with spin 1/2, the corresponding field supports both the particle and its antiparticle. This is a theorem in quantum field theory, not a hypothesis. It's provable from the basic axioms of the theory. If you accept that the universe obeys quantum mechanics and special relativity, then antiparticles must exist. There's no way around it. Some particles are their own antiparticles. The photon, for example, is its own antiparticle. So is the Z boson. These are particles whose quantum numbers are all 0, charge 0, lepton number 0, baryon number 0. When you flip all the signs, nothing changes. The particle is identical to its antiparticle. But for particles with non-zero quantum numbers, like the electron with its charge of -1 and lepton number of +1, the antiparticle must be distinct. It must have opposite values for all those numbers. And that distinct antiparticle is the positron. Now, let's talk about the symmetry that ties all of this together, because it's one of the most beautiful ideas in all of physics. It's called CPT symmetry. The C stands for charge conjugation, the P stands for parity, and the T stands for time reversal. Each of these represents a transformation you can apply to a physical system. Charge conjugation means replacing every particle with its antiparticle, flipping every charge, reversing every lepton number, swapping every quark for an antiquark. Essentially, replacing all matter with antimatter and all antimatter with matter. Parity means reflecting space, flipping left and right, turning everything into its mirror image. If you held up a mirror to the universe, parity is what you'd see. Time reversal means running time backward, making every process happen in reverse. Particles that were moving forward now move backward. Reactions that were proceeding in one direction now proceed in the other. Each of these symmetries, taken individually, can be violated. Nature doesn't always obey C symmetry alone. The weak nuclear force, the force responsible for certain types of radioactive decay, violates C symmetry. If you replace all particles with antiparticles in a weak interaction, you don't get the same result. The weak force treats matter and antimatter differently. It's as though nature can tell the difference between the original and the copy, at least when the weak force is involved. Nature also violates P symmetry. The weak force distinguishes between left and right. It interacts with left-handed particles and right-handed antiparticles, but not the reverse. This is deeply strange. Most forces in nature don't care about handedness. Gravity pulls on left-handed and right-handed objects equally. Electromagnetism treats them the same. But the weak force has a preference. It knows left from right. This violation of parity was discovered in 1956 by physicists Tsung-Dao Lee and Chen-Ning Yang, who proposed it theoretically, and confirmed experimentally in 1957 by Qianxiong Wu in a landmark experiment involving the beta decay of cobalt-60. Wu cooled cobalt-60 atoms to near absolute zero and aligned their nuclear spins using a strong magnetic field. She then measured which direction the electrons flew when the cobalt nuclei decayed. If parity were conserved, the electrons should have gone equally in both directions relative to the spin axis. They didn't. More electrons flew in one direction than the other. Nature has a preference. Nature distinguishes left from right. This was one of the most shocking experimental results in 20th century physics. It shattered a symmetry that physicists had assumed was unbreakable. Even the combined CP symmetry, charge conjugation plus parity together, can be violated. This was discovered in 1964 by James Cronin and Val Fitch, who observed that certain particles called neutral kaons decayed in ways that violated CP symmetry. This discovery was so important that Cronin and Fitch received the Nobel Prize for it. CP violation has since been confirmed in other particle systems, including B mesons and D mesons. But here's what's remarkable. Even though CP and CP can each be violated individually, the combination of all three, CPT, appears to be an exact symmetry of nature. If you simultaneously replace all particles with antiparticles, reflect space, and reverse time, you get a universe that obeys exactly the same physical laws as the original. No experiment has ever found a violation of CPT symmetry. And according to a deep mathematical result called the CPT theorem, proven in the 1950s, CPT symmetry must be exact in any quantum field theory that is consistent with special relativity and has a well-defined lowest energy state. Breaking CPT symmetry would require abandoning either quantum mechanics, special relativity, or both. Since both of these theories are confirmed to extraordinary precision, CPT symmetry is considered essentially inviolable. What does CPT symmetry mean for the positron? It means that if you take an electron, replace it with its antiparticle, the positron, reflect its spatial properties, and reverse its time direction, you get something that behaves exactly like the original electron. The positron is the electron seen through the CPT mirror. It's not just a particle with opposite charge, it's the electron transformed by the deepest symmetry we know of. This is why the positron must have exactly the same mass as the electron. CPT symmetry requires it. If the positron had even a slightly different mass, CPT symmetry would be violated, and the entire framework of quantum field theory would crumble. Physicists have tested this with incredible precision. The masses of the electron and positron agree to better than 1 part in a billion. Their charges agree to the same precision, but with opposite signs. Their magnetic moments agree to extraordinary accuracy. Every measurable property confirms CPT symmetry. The positron is the electron's CPT mirror image to the highest precision we can achieve. This is why calling the positron just an electron with opposite charge sells it short. The positron is the electron viewed through the most fundamental symmetry transformation in physics. It's the electron with every reversible property reversed. Not just charge, but lepton number, chirality, and the orientation of its magnetic moment relative to its spin. It is the complete inversion of the electron in every quantum mechanical sense. And this completeness of the inversion is precisely what allows annihilation to happen. When an electron and a positron come together, every quantum number cancels. Charge -1 plus +1 equals 0. Lepton number +1 plus -1 equals 0. Every conserved quantity adds to 0. There is nothing left to conserve except energy and momentum. The particles can convert entirely to photons because photons carry 0 charge, 0 lepton number, 0 everything that was being carried by the electron and positron. Nothing forbids this conversion. In fact, quantum field theory practically demands it. When a particle meets its antiparticle, when every quantum number has an exact opposite present, the state with both particles existing is quantum mechanically equivalent to a state with neither particle existing and radiation replacing them. The two states have the same total quantum numbers, 0 for everything. Quantum mechanics allows transitions between states with the same quantum numbers. So the transition happens. The particles annihilate. If any quantum number were not exactly opposite, annihilation couldn't happen the way it does. This is a critical point that most popular science descriptions gloss over. Consider a hypothetical particle that had the same mass as the electron and opposite charge, but the same lepton number, +1 instead of -1. Could it annihilate with an electron? No. The total lepton number before the event would be +2, 1 from the electron, and 1 from the hypothetical particle. After the event, photons have 0 lepton number. You can't go from a lepton number of 2 to 0 without violating conservation of lepton number. The reaction would be forbidden. The particles would interact electromagnetically, certainly. They'd attract each other because of their opposite charges. They might orbit each other. They might scatter off each other. But they couldn't annihilate completely. Something would have to be left behind to carry that excess lepton number. Debris, remnants, leftover particles. The clean, total destruction wouldn't happen. This is why the positron specifically, and only the positron, is the particle that annihilates with the electron. It's not because of charge alone, it's because every single conserved quantum number is exactly opposite. The cancellation is total, the balance is perfect, and perfect balance permits total annihilation. Let me take a moment to explain what it means for a field to have two modes of excitation, because this idea, once you grasp it, changes how you think about matter and antimatter entirely. Imagine a perfectly still lake. The surface of the lake is like a quantum field in its ground state, its lowest energy state. Nothing is happening. No particles exist. Now imagine you drop a stone into the lake. A ripple spreads outward. That ripple is like a particle. It's an excitation of the field, a disturbance that carries energy and moves through the medium. But here's the thing. The surface of the lake can also be disturbed in a different way. Instead of a crest, a raised bump of water, you could have a trough, a dip below the surface level. A crest and a trough are both disturbances of the same surface. They're both excitations of the same medium, but they're opposite in character. One goes up, the other goes down. If a crest and a trough of equal size meet, they cancel. The surface returns to stillness. The excitations are gone. This is, in a very rough sense, what happens with the electrons and positrons. The electron field can be excited in one mode, producing an electron. It can be excited in the opposite mode, producing a positron. When the two modes meet at the same point, they cancel. The field returns to its ground state. The excitations are gone. Energy is released as radiation, carried away by photons that ripple through the electromagnetic field. The electron field falls silent, and the electromagnetic field begins to sing. Now, I want to be careful here because this analogy has real limitations. Water waves are classical objects. Quantum fields obey the rules of quantum mechanics, dealing in probabilities, superpositions, and uncertainty. Real particle physics involves probability amplitudes, Feynman diagrams, and mathematics far more sophisticated than ripples on a lake. But the core insight holds. Particles and antiparticles are opposite excitations of the same field. They're not separate things that happen to cancel when they meet. They're complementary aspects of a single underlying reality. Two opposite disturbances that return the field to stillness when combined. This changes how you should think about the positron. It's not an alien intruder from some antimatter realm. It's not something fundamentally foreign to the electron. It is the electron field's other voice. The same field that produces every electron in every atom in your body also produces positrons. Every time a positron appears, the electron field is singing its other note. And when that note meets the first note, both fall silent. This understanding also explains why antiparticles were such a shock when first predicted. Before Dirac, physicists thought of particles as fundamental objects. The idea that every particle required a mirror image seemed extravagant. But quantum field theory showed that nature didn't double anything. There's one field for each type of particle, and that field naturally supports two modes of excitation. Antimatter isn't an addition to the universe. It's an inevitable consequence of how fields work. This inevitability makes the matter-antimatter asymmetry of the universe deeply puzzling. If electrons and positrons are just two modes of the same field, why does the universe contain vastly more electrons than positrons? The equations are symmetric. The universe is not, but that question belongs later. Right now, the crucial point is this. The positron is not merely an electron with a different charge. It is the electron's antiparticle in the deepest possible sense. It is the opposite excitation of the same quantum field. It carries opposite values for every conserved quantum number. It is the electron seen through the CPT mirror, the most fundamental symmetry in physics. And it is this total, complete, perfect opposition that makes annihilation possible. When every quantum number cancels, when every property has its exact opposite present, the particles can cease to exist entirely. Nothing forbids it. The laws of conservation are satisfied. The transition from particles to radiation is permitted. The positron is the universe's way of saying that for every disturbance, there exists an equal and opposite disturbance. For every particle, there exists an antiparticle. This is not a curiosity. It is a law woven into the fabric of quantum field theory, demanded by the combination of quantum mechanics and special relativity, and confirmed by every experiment ever performed. It means that matter carries within it the seed of its own annihilation. The same field that creates the electron also creates the positron. The universe has built into its fundamental structure the possibility of total cancellation, of matter and antimatter meeting and vanishing into light. And the consequence is breathtaking. It means that every electron in your body, every electron in every atom of every object you've ever touched, has a potential annihilator. Somewhere in the mathematics of the electron field, the positron waits as a possibility. An excitation that could, if created, unmake the electron completely. The universe doesn't just permit destruction. It has written the blueprint for the most complete form of destruction into the same equations that create the matter we're made of. So when we talk about what happens when a positron meets an electron, we're talking about two opposite excitations of the same field returning that field to silence. The energy locked up in the mass of both particles is released as radiation, and the field is quiet again. That process is what we need to examine next, because the mechanics of annihilation are even more extraordinary than you might imagine. So now we arrive at the event itself, the moment of contact. Everything we've talked about so far, the positron's opposite charge, its reverse quantum numbers, its nature as the electron's antiparticle, all of it has been building to this. What actually happens, physically, step by step, when a positron encounters an electron? How does the annihilation unfold? What does it look like if you could somehow slow it down and watch? Because the process isn't instantaneous. It isn't a single flash. There are stages, there's an approach, there's a capture. There's even briefly a strange and beautiful intermediate state where the two particles orbit each other, bound together in something that resembles an atom. And then there's the end. Total annihilation. Two particles reduced to nothing but light. Let's walk through it. It begins with attraction. The moment a positron enters any region of space containing ordinary matter, it's surrounded by electrons. They're in every atom, in every molecule, in the air, in solid surfaces, in liquids, in everything. And the positron, carrying a positive charge, is electromagnetically attracted to every one of them. This is the same fundamental force that holds atoms together. The same force that governs chemistry, electricity, and magnetism. The electromagnetic force between a positron and an electron follows Coulomb's law. The same inverse square law that governs the force between any two charged particles. The force is proportional to the product of the two charges divided by the square of the distance between them. Since the positron has a charge of +1 and the electron has a charge of -1, the product of their charges is negative, which means the force is attractive. They pull toward each other. At large distances, relatively speaking, the attraction is weak. If the positron is several nanometers from the nearest electron, the force exists, but it's modest. Other forces, thermal motion, collisions with other atoms, can easily overpower it. The positron bounces around, scattering off atoms in the material it has entered, losing kinetic energy with each collision. This is an important step. When a positron is first produced, say by radioactive decay, it typically has a lot of kinetic energy. It's moving fast, sometimes at a significant fraction of the speed of light. At these high speeds, the positron doesn't stop to interact with the first electron it passes. It blazes through matter, scattering off atoms, ionizing molecules, gradually slowing down. This process is called thermalization. The positron loses energy until it's moving at roughly the same speed as the thermal motion of the atoms around it. This takes a very short time, typically a few picoseconds in solid matter. A picosecond is 1/1,000,000th of a second. Once the positron has slowed down, it becomes vulnerable. It's no longer blazing past electrons too quickly to interact. Now, it's drifting through a sea of electrons at low speed, and the electromagnetic attraction has time to take hold. The positron begins to feel the pull of nearby electrons more strongly. It spirals inward toward one of them, but what happens next depends on what kind of matter the positron has entered, and this is something most descriptions leave out. The annihilation process is not identical in every material. In metals, the positron is repelled by the positively charged atomic nuclei and attracted into the spaces between atoms. It drifts through the crystal lattice until it finds a vacancy, a spot where an atom is missing from the structure. These defects act as traps. The positron falls into the vacancy and lingers there, surrounded by fewer electrons than normal, which actually extends its lifetime slightly before annihilation finally occurs. In gases, the situation is different. The positron can capture an electron from a gas molecule while still in motion, forming positronium in flight before it has fully thermalized. In liquids and some molecular solids, something stranger happens. The positronium atom, once formed, pushes away the surrounding molecules through a quantum mechanical effect called exchange repulsion, creating a tiny bubble around itself. The positronium sits inside this self-made cavity, a particle of antimatter carving out its own pocket of empty space in the heart of ordinary matter, before annihilation claims it. These differences are not minor curiosities, they're the basis of real experimental techniques that materials scientists use to probe the internal structure of metals, polymers, and semiconductors. And here's where something remarkable happens. Something that most people have never heard of. Before the positron and the electron annihilate, they can form a bound state. They can orbit each other, held together by electromagnetic attraction, in a structure that is eerily similar to a hydrogen atom. This structure is called positronium. Positronium is one of the strangest and most beautiful objects in all of physics. It's an atom, but not like any atom you've encountered before. In a normal hydrogen atom, a proton sits at the center and an electron orbits around it. The proton is about 1,836 times heavier than the electron, so it barely moves. The electron does all the orbiting. The proton just sits there, a massive anchor holding the electron in place, but in positronium, both particles have exactly the same mass. The electron and the positron are equal partners. Neither one is the anchor, neither one is the orbiter. They both orbit their common center of mass, circling each other in a delicate electromagnetic dance. Positronium has real, measurable properties. It has energy levels, just like hydrogen. It has a ground state and excited states. When it transitions between energy levels, it emits photons, just like a regular atom. Its radius is about twice the radius of a hydrogen atom, because the reduced mass of the system is half the electron mass, which causes the orbits to expand. Physicists have studied positronium extensively. They've measured its energy levels with incredible precision and found perfect agreement with the predictions of quantum electrodynamics. Positronium is a triumph of theoretical physics. It's also unique in ways that no other atom can match. Positronium is the lightest known atom, with a total mass of only about 1,000th of the mass of hydrogen, and it has no nucleus. Every other atom in the universe has a heavy nucleus at its center, made of protons and neutrons, with electrons orbiting around it. Positronium has nothing at the center. 2 equal mass particles orbiting empty space. It is purely leptonic, made entirely of leptons with no baryonic matter involved at all. Physicists have even gone further. In 2007, a team at the University of California, Riverside, confirmed the existence of dipositronium, a molecule made of 2 positronium atoms bonded together. 2 electrons and 2 positrons, bound by electromagnetic forces into a 4-particle system. It lasted only about half a nanosecond before all 4 particles annihilated, but it was real. A molecule made entirely of matter and antimatter, briefly existing before vanishing into gamma rays. But positronium is also doomed. Unlike hydrogen, which is stable and can exist forever, positronium is inherently unstable. Not because something is wrong with it structurally, but because the 2 particles it's made of are each other's antiparticles. They will annihilate. It's not a question of whether, it's a question of when. And the when depends on how the positronium is configured. Positronium comes in 2 forms, depending on how the spins of the electron and positron are aligned. Spin, remember, is a quantum property that every electron and positron possesses. It's an intrinsic angular momentum, somewhat analogous to a tiny particle spinning on its axis. Though that mental picture is misleading because particles aren't actually little spinning balls. Spin is a purely quantum mechanical property with no true classical equivalent. Each particle has a spin of 1/2, and that spin can point in one of 2 directions relative to any chosen axis, usually called up and down. In positronium, the electron and positron can have their spins aligned in the same direction, both up or both down, or in opposite directions, one up and one down. When the spins are opposite, the total spin of the system is 0. This configuration is called parapositronium. When the spins are aligned in the same direction, the total spin of the system is 1. This configuration is called orthopositronium. The distinction matters enormously because it determines how the annihilation proceeds. Parapositronium, with its total spin of 0, annihilates into 2 gamma-ray photons. This happens extremely quickly. The mean lifetime of parapositronium is about 125 picoseconds. That's 125 trillionths of a second. In that brief flicker of time, the electron and positron orbit each other, and then they're gone. 2 photons emerge, flying off in exactly opposite directions. Orthopositronium, with its total spin of 1, cannot annihilate into 2 photons. This is because of conservation of a quantity called charge conjugation parity, or C parity for short. 2 photons have a combined C parity of +1. Orthopositronium has a C parity of -1. The values don't match, so the decay into 2 photons is forbidden. Instead, orthopositronium must annihilate into 3 photons, or 5, or some other odd number. 3 is by far the most likely, because higher numbers of photons are increasingly improbable. The need to produce 3 photons instead of 2 makes the process slower. Orthopositronium has a mean lifetime of about 142 nanoseconds. That's roughly 1,000 times longer than parapositronium. Still incredibly short by human standards, but a relative eternity in the world of particle physics. These lifetimes have been measured with exquisite precision, and they match the theoretical predictions of quantum electrodynamics to many decimal places. This agreement is one of the strongest confirmations of our understanding of how matter and antimatter interact. The theory doesn't just predict that annihilation happens, it predicts exactly how fast it happens, to within a fraction of a percent. And the experiments confirm those predictions. Now let's focus on the annihilation itself, starting with the most common case, positronium decaying into 2 gamma-ray photons. This is the process that occurs in PET scans, and it's the cleanest, most elegant example of antimatter annihilation. The electron and the positron come together. Their quantum numbers cancel. Charge, -1 plus +1 equals 0. Lepton number, +1 plus -1 equals 0. Every conserved quantum number adds up to 0. What's left is mass and energy. The combined rest mass of the electron and positron must go somewhere. It can't just disappear. Energy is conserved. Mass is a form of energy, as Einstein showed with E equals mc². The rest mass energy of an electron is about 511,000 electron volts. The rest mass energy of a positron is also about 511,000 electron volts, since they have the same mass. The total rest mass energy of the system is therefore about 1,022,000 electron volts, or approximately 1.022 mega electron volts. This energy must be carried away by the products of the annihilation. In the case of positronium at rest, those products are 2 photons. Each photon carries away half the total energy, so each one has an energy of about 511,000 electron volts. This is a very specific, very precise energy. It's a signature, a fingerprint of electron-positron annihilation. When physicists detect a photon with an energy of exactly 511,000 electron volts, they know it almost certainly came from a positron meeting an electron. This is how PET scanners work. They look for pairs of photons, each with this characteristic energy, arriving at detectors on opposite sides of the patient at the same time. The coincidence of 2 511,000 electron volt photons arriving simultaneously tells the machine that an annihilation happened somewhere along the line between the 2 detectors. But why 2 photons? Why not 1? This is where conservation of momentum enters the picture. Momentum is a measure of how much motion an object has. It depends on both the object's mass and its velocity. In any physical process, the total momentum before the event must equal the total momentum after the event. This is one of the most fundamental conservation laws in physics. Consider what would happen if the annihilation produced just 1 photon. Before the annihilation, if the positronium is at rest, the total momentum of the system is 0. The electron and positron are orbiting each other, but the center of mass isn't going anywhere. Total momentum, 0. If only 1 photon were produced, that photon would carry momentum. Photons always carry momentum. A single photon moving in one direction has non-zero momentum, but the total momentum before the event was 0. A single photon can't have 0 momentum, so a single photon would violate conservation of momentum. It's forbidden. 2 photons solve this problem elegantly. If 2 photons are emitted in exactly opposite directions, their momenta are equal in magnitude, but opposite in direction. They cancel. The total momentum of the 2 photons is 0, matching the 0 total momentum of the original positronium. Conservation of momentum is satisfied. This is why, in the rest frame of positronium, the 2 photons always fly off in exactly opposite directions. They have to. The mathematics of conservation laws demands it. If you detect one photon going to the left, you know with certainty that another photon of the same energy went to the right. This back-to-back emission is not a coincidence. It's a requirement of the laws of physics. Now let's talk about why the photons are gamma rays specifically. The type of photon is determined entirely by its energy. Visible light photons carry about 2 electron volts. X-rays carry a few thousand. The annihilation photons carry 511,000 electron volts each, which is firmly in the gamma ray range. This is fixed by the mass of the electron. You can't change it. The mass determines the energy, and that energy corresponds to gamma rays, the most energetic and penetrating form of electromagnetic radiation. Gamma rays can pass through solid walls, through metal, through human tissue. In medical PET scans, the gamma rays pass right through the patient's body and are detected by sensors arranged in a ring. If they couldn't penetrate tissue, the technique wouldn't work. Let me now describe the annihilation in a slightly different way to make sure the full strangeness of it comes through. Before the annihilation, you have 2 particles. 2 things with mass, with charge, with spin, with lepton number. They have definite positions in space. They're moving, interacting with their environment. They are, in every meaningful sense, real physical objects. They exist. After the annihilation, they don't exist. They're gone. Not moved somewhere else, not transformed into other particles with mass. Gone. In their place are 2 photons, massless particles of light, racing away from the point of annihilation at the speed of light. The photons carry the energy that was locked up in the mass of the electron and positron, but they carry none of the properties that define those particles. The photons have no electric charge, they have no lepton number, they have no rest mass. The only things they carry are energy, momentum, and spin. Specifically a spin of 1 each. Everything else, the charge, the lepton number, the identity of the original particles, is gone. Erased. The information about what was there before is not preserved in any recoverable form. This is not like any other form of destruction we encounter in everyday life. When you burn a log in a fireplace, the log is destroyed as a log, but the atoms aren't gone. They've been rearranged into carbon dioxide, water vapor, and ash. If you had enough patience and the right equipment, you could, in principle, gather all the combustion products and reconstruct the original log molecule by molecule. The matter is conserved. It's just been rearranged. When a star explodes as a supernova, the destruction is catastrophic. The star is blown apart, its material scattered across light years of space. But the atoms that made up the star survive. They become nebulae that form new stars and planets. The matter persists, but matter-antimatter annihilation is different. The particles themselves are gone, not rearranged, not scattered, eliminated. The mass that defined them has been converted entirely into energy. The photons carry energy, but they don't carry the mass, charge, or identity of the original particles. The destruction is total, complete, and irreversible in a way that no other physical process matches. Now, I should be precise here. In principle, the reverse process can happen. 2 gamma-ray photons with enough energy can collide and produce an electron-positron pair. This is called pair production, and it's been observed in laboratories and happens naturally near strong fields. So the laws of physics allow the reverse. But in practice, pair production requires very specific conditions, and the probability of 2 specific annihilation photons recombining to form the same electron-positron pair is so astronomically small that it will never happen. The information about the original particles is lost for all practical purposes. Let me talk about the energy involved. The total mass being annihilated in a single event is about 1.8 to 2 times 10 to the negative 30 kilograms. Using E equals mc squared, the total energy released is about 1.022 million electron volts. That doesn't sound like much. And for a single event, it isn't. It's negligible on human scales, but that tiny amount of energy represents 100% conversion of mass to energy. Every last fraction of the mass has been turned into radiation. No other process achieves this. Nuclear fission, the process that powers nuclear reactors and atomic bombs, converts roughly 0.09% of mass to energy. It's enough to power cities or destroy them, but it's a tiny fraction of the total mass involved. Nuclear fusion, the process that powers the sun and hydrogen bombs, does better. When 4 hydrogen nuclei fuse to form one helium nucleus, about 0.7% of the mass is converted to energy. That's about 8 times more efficient than fission, which is why fusion releases more energy per unit of fuel. But it's still less than 1%. Matter-antimatter annihilation converts 100%, not 0.7%, not 0.09%, 100%. Every particle of mass becomes energy. Nothing is wasted. Nothing remains. This makes matter-antimatter annihilation the most energetically efficient process allowed by the laws of physics. Nothing in the universe extracts more energy per unit of mass. To put this in perspective, if you could annihilate 1 kilogram of matter with 1 kilogram of antimatter, you would release about 1.8 times 10 to the 17 joules of energy. That's close to the energy released by the largest nuclear weapon ever detonated, the Tsar Bomba, which had a yield of about 50 megatons of TNT, from just 2 kilograms of material. The Tsar Bomba weighed about 27 metric tons. Matter-antimatter annihilation would produce comparable energy from a mass roughly 14,000 times smaller. 1 kilogram of antimatter annihilating with 1 kilogram of matter would produce enough energy to power the entire United States for roughly half a day, based on total average energy consumption from 2 kilograms of fuel. This is the power of E equals mc squared when you convert all of the mass, not just a tiny fraction. Of course, we can't actually do this in practice. Producing antimatter is extraordinarily difficult and expensive. The total amount of antimatter ever produced by all the particle accelerators in the world combined amounts to just a few nanograms. And storing it is equally challenging because it annihilates on contact with any ordinary matter. But the theoretical energy density of matter, antimatter annihilation, is unmatched by anything else in physics. Let's return to the annihilation event and examine one more detail. In practice, the positronium is rarely perfectly at rest. It has some residual thermal motion. This means the 2 photons are not emitted at exactly 180 degrees. There's a slight deviation, typically less than a degree. In PET scans, this small angular spread is one of the factors that limits the spatial resolution of the image. The photon energies also shift slightly due to the Doppler effect, one photon gaining a tiny amount of energy and the other losing the same amount. Physicists use these subtle variations as diagnostic tools. Positron annihilation spectroscopy exploits these effects to study defects in metals and semiconductors, making antimatter physics a practical tool in material science. The 3-photon annihilation of ortho-positronium is also well studied. For free electron-positron annihilation, the predicted ratio of 3-photon to 2-photon events is about 1 to 370, a calculation first performed by Orr and Powell. Experiments have confirmed this with high precision. Every agreement between prediction and measurement strengthens our confidence that we truly understand the physics of matter-antimatter annihilation. Let me step back now and emphasize the central fact one more time, because it's easy to get lost in the details and miss the staggering simplicity of what's happening. Two particles meet. They have opposite quantum numbers in every respect. They attract each other, spiral inward, briefly form a bound state, and then cease to exist. Their mass becomes energy. Every quantum number that defined them cancels against its opposite. Everything about them that made them particles, that gave them identity, that made them real physical objects with definite properties, all of it vanishes. What's left is radiation, photons, massless packets of energy traveling at the speed of light. No debris, no remnants, no ash, no fragments, just light. This is the most complete form of destruction that the laws of physics permit. You cannot destroy something more thoroughly than this. In every other process, something survives. Atoms survive chemical reactions. Nuclei survive most nuclear reactions. Quarks survive the strongest particle collisions. But in matter-antimatter annihilation, nothing survives. The particles are gone. Their mass is gone. Only energy remains, carried by photons that will travel across the universe until they're absorbed by something else. And this process is not theoretical. It's not hypothetical. It happens trillions of times every day on Earth alone. Every time a radioactive atom undergoes beta plus decay and emits a positron, that positron finds an electron within nanoseconds and annihilates. Every PET scan performed in every hospital on every continent produces millions of these annihilation events inside patients' bodies. Cosmic rays striking the atmosphere create positron-electron pairs that immediately annihilate. The process is happening right now, all around you, constantly. The universe is quietly, ceaselessly, performing the most efficient energy conversion process known to physics. Particles and antiparticles meeting, cancelling, and vanishing into light. There's something almost violent about the elegance of it. Two particles, each perfectly stable on its own, each capable of existing forever in isolation, meet and are instantly unmade. Not because either one is flawed, not because either one is unstable, but because together they possess the exact combination of properties that the laws of physics allow to vanish. Their existence is permitted. Their coexistence is not. The universe creates both, but it cannot sustain both in the same place. The question that naturally follows is why? Why does ordinary matter erase the positron so effectively? Why can't the positron survive in our world? Why is the universe arranged in such a way that positrons are destroyed almost the instant they appear? The answer lies not in the positron itself, which would last forever in empty space, but in the universe we live in. A universe made overwhelmingly of matter. A universe full of electrons with no corresponding abundance of positrons to balance them. A universe that, for reasons we still don't fully understand, chose matter over antimatter billions of years ago. And that asymmetry, that cosmic imbalance, is what condemns every positron that appears in our world to a fleeting existence and an inevitable end. So why does matter erase the positron? We have seen the mechanism in detail. We know that when a positron meets an electron, their opposite quantum numbers cancel, and both particles are annihilated into gamma rays. But why is this so inevitable? Why can't a positron survive in our world for more than a fleeting instant? The answer isn't complicated, but it is profound. And it leads to one of the deepest unsolved mysteries in all of physics. The reason matter destroys positrons so efficiently is almost embarrassingly simple. Ordinary matter is full of electrons, not just sprinkled with them, saturated with them. Every atom in the universe contains electrons. A single atom of hydrogen, the simplest element, has 1 electron. A single atom of iron has 26. A single atom of uranium has 92. The air you're breathing right now contains roughly 10 to the 25th molecules per cubic meter. Each molecule contains multiple electrons. A cubic meter of air at sea level contains something like 10 to the 26 electrons, give or take. 100 trillion electrons in a volume the size of a large suitcase. Solid matter is even denser. A cubic centimeter of copper, smaller than a sugar cube, contains roughly 8.5 times 10 to the 22 atoms, each with 29 electrons. That tiny cube of metal holds approximately 2.5 times 10 to the 24 electrons. 2.5 trillion electrons packed into a volume smaller than your fingertip. Now imagine you're a positron. You've just been created by some process, maybe radioactive decay, maybe a cosmic ray collision. You enter this environment. You're a single particle with positive charge, surrounded on all sides by an ocean of electrons. Trillions upon trillions of them in every cubic centimeter of matter around you. Each one carries the opposite charge. Each one attracts you electromagnetically. Each one has quantum numbers that are the exact opposite of yours. Each one is capable of annihilating you completely. You don't have to go looking for an electron. You can't avoid them. They're everywhere. They're in the air. They're in the ground. They're in the walls. They're in the molecules of every substance you could possibly encounter. The density of electrons in ordinary matter is so enormous that a positron entering any material will encounter an electron almost immediately. Whether it takes 100 picoseconds or a few nanoseconds depends on the material, but the outcome is always the same. The positron finds an electron. The two particles annihilate. The positron ceases to exist. This is what we mean when we say matter erases the positron. The positron doesn't join an atom, it doesn't become part of a molecule, it doesn't settle into any stable configuration. It meets an electron and both particles vanish. The positron is not absorbed or neutralized, it's annihilated. The particles don't combine into something new. They cancel each other completely. Nothing remains except energy in the form of radiation. The positron's destruction is a direct consequence of living in a universe made of matter. If the universe contained equal amounts of matter and antimatter, well distributed and mixed together, there would be no electrons for the positron to annihilate with, because the electrons would have already annihilated with positrons. Everything would have cancelled out long ago, but that's not the universe we live in. Our universe is made overwhelmingly of matter. For every antiparticle in the observable universe, there are roughly 1 billion particles of ordinary matter. This enormous imbalance means that any positron created in our universe is immediately surrounded by a vast surplus of electrons. It has no chance of survival. The matter wins every single time. Let's talk about where positrons actually come from, because understanding their sources makes it even more striking how quickly they vanish. Positrons are produced through several natural processes, and none of them are rare or exotic. They're happening all around you right now. The most straightforward source is beta plus decay. Certain radioactive isotopes decay by converting a proton in the nucleus into a neutron. When this happens, the excess positive charge is carried away by a positron, along with an electron neutrino. This process is governed by the weak nuclear force, the same force responsible for other types of radioactive decay. Isotopes that undergo beta plus decay include carbon-11, nitrogen-13, oxygen-15, fluorine-18, potassium-40, and sodium-22, among many others. Some of these are naturally occurring. Potassium-40, for example, is present in soil, rocks, seawater, and in your own body. About 0.012% of all naturally occurring potassium is the radioactive isotope potassium-40. Your body contains about 140 grams of potassium. Of that, about 17 milligrams is potassium-40. And a small fraction of that potassium-40, about 0.001% of its decays, undergoes beta plus decay, producing a positron. The rest decays through other channels. This means your body is producing positrons right now, at this moment. Not many. Perhaps a few thousand per day. Each one survives for less than a nanosecond before finding an electron in your tissue and annihilating. You are a site of continuous matter-antimatter annihilation, and you've never noticed. Cosmic rays are another significant source. When high-energy protons and atomic nuclei from space strike molecules in Earth's upper atmosphere, the collisions produce showers of secondary particles. These showers can contain hundreds or thousands of particles cascading downward through the atmosphere. Among the particles produced are electron-positron pairs, created through a process called pair production. In pair production, the kinetic energy of the colliding particles is transformed into mass through the same E equals mc squared equivalence that governs annihilation. The energy becomes two particles, one electron and one positron, conjured out of pure energy and the presence of a nearby atomic nucleus. The positron created in this way flies through the atmosphere at high speed, scattering off air molecules, ionizing atoms along its path, losing energy with each interaction, and eventually slowing down enough for an electron to capture it. Annihilation follows. The gamma rays produced are absorbed by the atmosphere or continue into space, carrying away the energy that was briefly locked in the mass of two doomed particles. Thousands of these events happen in Earth's atmosphere every second. Every moment of every day, cosmic rays are creating positrons high above your head, and those positrons are being destroyed by the matter in the atmosphere almost as fast as they appear. There's also pair production near strong electromagnetic fields. When a high-energy gamma ray passes close to a heavy atomic nucleus, the intense electric field of the nucleus can cause the photon to convert into an electron-positron pair. The photon disappears, and two particles appear in its place. This happens in particle accelerators, in the atmospheres of neutron stars, in the accretion disks around black holes, and anywhere else where high-energy photons encounter strong fields. In these extreme environments, positrons can be produced in enormous quantities. The jets streaming from active galactic nuclei, powered by supermassive black holes consuming matter, are thought to contain substantial numbers of positrons. Pulsars, rapidly rotating neutron stars with incredibly strong magnetic fields, produce cascades of electron-positron pairs in their magnetospheres. In these exotic cosmic environments, positrons are common, but even there, in the jets of black holes and the magnetic fields of pulsars, the positrons don't survive forever. Eventually they encounter electrons and annihilate. The gamma rays from these annihilation events can be detected by space telescopes. Astronomers use the 511,000 electron volt gamma ray line as a diagnostic tool, a way to detect positron annihilation happening in distant astrophysical environments. There's a particularly fascinating source of positrons right at the center of our own galaxy. Observations by gamma ray telescopes, particularly the Integral satellite operated by the European Space Agency, have detected a strong 511,000 electron volt emission from the central region of the Milky Way. This tells us that enormous numbers of positrons are being produced and annihilated near the galactic center. The rate is staggering. Roughly 10 to the 43rd positrons annihilate every second in the central region of the galaxy. That's 10 million trillion positrons destroyed every second, each one meeting an electron in the interstellar gas and vanishing into gamma rays. The source of these positrons is still debated. They might come from radioactive decay of elements like aluminium-26 and titanium-44 produced in supernovae and distributed through the interstellar medium. They might come from interactions involving the supermassive black hole, Sagittarius A star at the galaxy's center. They might come from a type of stellar remnant called a low-mass six-ray binary, where matter from a normal star falls onto a neutron star or black hole, and the extreme conditions produce electron-positron pairs. Some physicists have even speculated that the positrons could come from the annihilation or decay of dark matter particles, which would make this gamma-ray signal a potential window into one of the universe's other great mysteries. The mystery of the galactic positron excess is an active area of research, with new observations and theories appearing regularly. But whatever is producing them, the positrons don't last long. They find electrons in the interstellar gas and annihilate, producing the gamma ray glow that our telescopes detect from half a galaxy away. Every one of these sources produces positrons that are destroyed almost immediately in our matter-dominated universe. The positrons don't accumulate. They don't build up over time. They flash into existence and vanish, leaving behind only gamma rays as evidence that they ever existed. The universe is constantly creating antimatter and constantly erasing it. Production and destruction in an endless cycle with matter, always winning because matter is overwhelmingly more abundant. And this brings us to the deepest question of all. The question that has haunted physicists for decades. The question that the positron forces us to confront every time we think carefully about what it is and what it means. If the laws of physics treat matter and antimatter symmetrically, why is the universe made almost entirely of matter? This is not a trivial question. It's not a minor puzzle or a small gap in our understanding. It may be the single most important unanswered question in all of cosmology. Because if the laws of physics are truly symmetric between matter and antimatter, and every experiment we've ever conducted suggests they very nearly are, then the Big Bang should have produced exactly equal amounts of matter and antimatter, equal numbers of electrons and positrons, equal numbers of protons and antiprotons, equal numbers of neutrons and antineutrons, every quark paired with an antiquark, every lepton paired with an antilepton. A universe born in perfect symmetry. And then, within the first few seconds of the universe's existence, As temperatures dropped low enough for particles to slow down and interact, all of that matter and antimatter should have found each other and annihilated. Every particle should have met its antiparticle. Every electron should have met a positron. Every proton should have met an antiproton. The cancellation should have been total and merciless. The universe should have been left with nothing but a sea of radiation. No matter, no antimatter, no atoms, no molecules, no stars, no planets, no chemistry, no biology, no life, no consciousness, just photons. An eternal, featureless bath of cooling light expanding into the void forever, with nothing solid or complex in it. Nothing interesting, nothing alive. Just light fading toward absolute cold for all eternity. But that's not what happened. Something went wrong, or rather, something went right. Somehow, in the first fraction of a second after the Big Bang, a tiny imbalance developed between matter and antimatter. For every billion antimatter particles, there were 1,000,000,001 matter particles. One extra matter particle for every billion. That's the imbalance. 1 part in a billion. It's tiny. It's almost nothing, but was enough. When the matter and antimatter annihilated in the early universe, the billion antimatter particles cancelled the billion matter particles, releasing enormous amounts of energy. But that one extra matter particle had no antimatter partner. It survived. Multiply this by the unimaginable number of particles in the early universe, and you get the matter that makes up everything you see today. Every galaxy, every star, every planet, every living thing, all of it is that leftover 1 in a billion residue. We are the crumbs left over from the greatest annihilation event in the history of the cosmos. The evidence for this is written in the cosmic microwave background, the faint glow of radiation left over from the Big Bang that fills the entire universe. The number of photons in the cosmic microwave background compared to the number of matter particles tells us the ratio of the original imbalance. For every proton or neutron that exists today, there are about 1.6 billion cosmic microwave background photons. Those photons are the remnants of the annihilations. They're the ashes of the matter and antimatter that destroyed each other. And everything we see, everything that exists as solid matter, we're the tiny leftover. In 1967, the Soviet physicist Andrei Sakharov identified 3 conditions that must be met for a matter-antimatter asymmetry to develop from an initially symmetric universe. These are now called the Sakharov conditions, and they provide a framework for understanding how the asymmetry might have arisen. The first condition is baryon number violation. There must exist some process that can change the total number of baryons, which are particles like protons and neutrons. If baryon number is always perfectly conserved, if the total number of matter particles minus the total number of antimatter particles is always exactly the same, then the number of matter particles can never come to differ from the number of antimatter particles. Something has to break this conservation law, at least slightly, at least briefly, at least under the extreme conditions of the early universe. The second condition is C and CP symmetry violation. The processes that violate baryon number must treat matter and antimatter differently. If every reaction that creates an excess of matter has an equally probable counterpart that creates an equal excess of antimatter, no net asymmetry develops. The universe's rulebook must be slightly biased. Not dramatically, just by 1 part in a billion. But the bias must be there. The third condition is departure from thermal equilibrium. If the universe is in perfect equilibrium, Every forward reaction is balanced by its reverse, and any asymmetry generated is immediately erased. The universe must be changing rapidly, cooling and expanding faster than the reactions can keep up with. The first fractions of a second after the Big Bang provided exactly this kind of non-equilibrium environment, where asymmetries could become frozen in before reverse reactions could undo them. We know that all three of Sakharov's conditions are met to some degree in the standard model of particle physics. Baryon number violation can occur through subtle quantum processes called sphalerons, which are important at very high temperatures like those in the early universe. CP violation has been observed in the decay of certain particles, the kaons and B mesons I mentioned earlier. And the rapid expansion of the universe after the Big Bang provides the departure from equilibrium. But here's the problem. The amount of CP violation in the standard model is too small, way too small. When physicists calculate the matter-antimatter asymmetry that would result from the known CP violation in the standard model, combined with the known baryon number, violating processes, and the known expansion rate of the early universe, they get an asymmetry that is many orders of magnitude smaller than what we observe. The standard model can explain a tiny preference for matter over antimatter, but not nearly enough to account for the universe we see. Something beyond the standard model must be responsible. This is one of the strongest pieces of evidence that the standard model is incomplete. There must be physics beyond the standard model that generates enough CP violation to produce the observed asymmetry. Several theories attempt to explain this. Leptogenesis proposes that the asymmetry originated in the neutrino sector and was then converted to a baryon asymmetry. Electroweak baryogenesis proposes it was generated during the electroweak phase transition in the first trillionth of a second after the Big Bang. Affleck-Dine baryogenesis invokes the dynamics of scalar fields in the early universe. Each theory makes different predictions. None has been confirmed. The origin of the matter-antimatter asymmetry remains one of the great unsolved problems in physics. Experiments around the world are searching for answers. At CERN, the LHCb experiment studies the decays of B mesons and other heavy particles, searching for CP violation beyond what the standard model predicts. At laboratories in Japan, the United States, and Europe, neutrino experiments send beams of neutrinos and antineutrinos over long distances, measuring whether they oscillate differently. If they do, it will be direct evidence of CP violation in the lepton sector, potentially supporting leptogenesis as the mechanism behind the asymmetry. Early results have shown hints, but the data is not yet conclusive. The next generation of experiments will provide definitive measurements. The alpha and base experiments at CERN are studying antihydrogen, atoms made of an antiproton and a positron, comparing their properties to ordinary hydrogen with extraordinary precision. Any difference, no matter how small, would signal a violation of CPT symmetry and would revolutionize physics. So far, no difference has been found. Antihydrogen appears to behave identically to hydrogen in every way that's been tested. The symmetry holds, and the mystery deepens. Think about what this means. The positron exists because the laws of physics demand it. The symmetry between matter and antimatter is exact, as far as we can tell. And yet, the universe itself is not symmetric. The positron, which should be just as common as the electron, is instead vanishingly rare, destroyed by the overwhelming surplus of electrons that fill the cosmos. We exist because this asymmetry exists. If the laws of physics were perfectly symmetric in practice and not just in theory, if the Big Bang had produced exactly equal amounts of matter and antimatter, then everything would have annihilated. The universe would be nothing but radiation. No structures, no complexity, no life, no consciousness, no one to ask why. The fact that you're here, listening to this, thinking about positrons and annihilation and the origin of matter, is a direct consequence of a tiny asymmetry, 1 part in a billion, that emerged in the first moments of the universe's existence for reasons we still do not understand. Your existence is not guaranteed by the laws of physics. It is permitted only because those laws were broken, or more precisely, because some deeper law that we haven't yet discovered slightly favored matter over antimatter at the moment of creation. The positron is a messenger from this deeper reality. Its existence tells us that the laws of physics are symmetric. Its absence from the everyday world tells us that something broke that symmetry. Every time a positron is created by radioactive decay or cosmic ray collision and then destroyed by the surrounding matter, it's reenacting in miniature the great drama that played out at the birth of the universe, matter and antimatter meeting, annihilating, and matter winning, simply because there's more of it. Not because matter is stronger, not because matter is better, not because the laws of physics favor matter over antimatter, but because some unknown process, some physics we haven't yet discovered, tip the scales by 1 part in a billion at the very beginning. The positron lives and dies as a reminder of this. It is born into a universe where it has no place, surrounded by the descendants of the matter that survived the great annihilation. It exists for a few nanoseconds, then vanishes, just as its ancestors did 13.8 billion years ago, when the universe was young and the annihilation was still underway. That 1 part in a billion is everything. It's every star you see in the night sky. It's every galaxy, every planet, every mountain and ocean and forest on Earth. It's every person who has ever lived or ever will live. It's the air in your lungs and the thoughts in your brain and the light reaching your eyes as you hear these words. All of it exists because the universe produced slightly more matter than antimatter in its first moments. Slightly more electrons than positrons. Slightly more protons than antiprotons. And everything that didn't have a partner annihilated, leaving behind the cosmic microwave background as a monument to all the matter and antimatter that was lost, and leaving behind the material universe as the tiny, precious surplus that remained. So, the next time you hear the word positron, remember what it really means. It's not just a particle with opposite charge, it's the electron's perfect mirror. It's quantum opposite. It's antimatter twin. It's a particle that is perfectly stable on its own, that would last forever in empty space, but that is condemned to instant destruction in our matter-dominated world because the universe is full of electrons waiting to annihilate it. It's a particle whose existence proves that the laws of physics are symmetric between matter and antimatter, and whose absence from everyday life proves that something shattered that symmetry at the dawn of time. It's a particle that reminds us that we shouldn't be here, that the universe should be empty, that the existence of everything we see and know and love depends on a tiny cosmic accident, a 1 in a billion imbalance that no one can yet explain. The positron is real. Matter really does erase it. And the reason matter can erase it, the reason there's enough matter to erase every positron that appears, is the greatest mystery in the history of the universe. We are the aftermath of an asymmetry we do not understand, living in a cosmos that should have annihilated itself into nothingness billions of years ago. And yet here we are, made of matter, surrounded by matter, thinking about the antimatter that almost prevented us from existing, asking questions about our own origins that the universe itself seems reluctant to answer. That's what a positron really is. And that's why matter erases it. And that's why the fact that anything exists at all is the most astonishing thing about the universe. Thank you for joining me on this journey tonight. If you found this exploration valuable, a like or subscribe would mean a lot. It helps keep these deep dives into the nature of the universe coming. The positron is small, fleeting, and doomed from the moment it appears. But what it tells us about the universe is vast. Every time you look around at the world, at anything solid, anything real, anything made of atoms, remember that you're looking at the survivors, the leftovers, the 1 in a billion particles that had no antimatter partner to annihilate them. You exist because the universe was just slightly imperfect. And that imperfection is the most beautiful thing in all of physics. Good night.